block cipher out of arbitrary functions f1 to fd. Okay, so imagine we have these functions f1 to fd that happens to map n bits to n bits. Now these are arbitrary functions. They don't have to be invertible or anything. What we want to do is build an invertible function out of those d functions. And the way we'll do it is by building a new function, we'll call it capital F, that maps 2n bits to 2n bits. And the construction is described right here. So here we have our input. You notice there are 2 blocks of n bits. In other words, the input is actually 2n bits. R and L stand for right and left. Typically people describe a Feistel network from top to bottom, in which case these n bits really would be right and left. But here it's more convenient for me to describe it horizontally. So if we follow the R input, you realize it basically gets copied into the L output without any change at all. Okay? However, the L input is changed somewhat. Basically what happens is the R input is fed into the function f1, and the resultant is XORed with L0, and that becomes the new R1 input. Okay, so this is called one round of a Feistel network, and it's done using the function f1. Now we do this again with another round of the Feistel network with the function f2, and we do it again and again and again till we get to the last round, and we do it again with the function fd, and finally the output is rd ld. Okay, so if you like, we can write this in symbols, that basically li is simply equal to ri minus 1, and ri, let's see, that's the more complicated one, ri is equal, well, let's just follow the lines here, ri is just equal to fi applied to ri minus 1 XOR li. Okay, so and this is basically I goes from 1 to d. So this is the equation that defines a Feistel network mapping a 2n-bit input to 2n-bit output. So here we have the, again, I just copied the picture of the Feistel network, and the amazing claim is that in fact it doesn't matter which functions you give me. For any functions f1 to fd that you give me, the resulting Feistel network function is in fact invertible. And the way we're going to prove that is basically we're going to construct an inverse, because not only is it invertible, it's efficiently invertible. So let's see. So let's look at one round of a Feistel network. So here, this is the input, Ri, Li, and this is the output, Ri plus 1, Li plus 1. And now what I'm going to ask you is to invert this. So let's see. So suppose now the input that we're given is Ri plus 1, Li plus 1. And we want to compute Ri, Li. So we want to compute the round in the reverse direction. So let's see if we can do it. Well, let's look at Ri. So Ri is very easy. Basically, Ri is just equal to Li plus 1. So Li plus 1 just becomes Ri. But now let me ask you to write the expression for Li in terms of Ri plus 1 and Li plus 1. So I hope everybody sees that basically Li plus 1 is fed into the function Fi plus 1. The result is XORed with Ri plus 1, and that gives the Li input. So this is the inverse of one round of a Feistel network. And if we draw this as a diagram, let's just write the picture for the inverse. So here you notice the input is Ri plus 1, Li plus 1, and the output is Ri, Li, right? So we're inverting the round. So you notice that the inverse of a Feistel round looks pretty much the same as the Feistel round in the forward direction. It's literally, just for a technical reason, it's kind of the mirror image of one another, but it's basically the same construct. And when we put these inverted rounds back together, we essentially get the inverse of the entire Feistel network. So you notice we start off with round number d, with the inverse of round number d, then we do the inverse of round number d minus 1, and so on and so forth, until we get to the inverse of the first round, and we get our final output, which is R0, L0. Right? This is the input, and we manage to invert basically RD, LD and get R0, L0. And the interesting thing is that basically the inversion circuit looks pretty much the same as the encryption circuit, and the only difference is that the functions are applied in reverse order. Right? We started with FD and ended with F1, whereas when we were encrypting, we started with F1 and ended with FD. So for hardware designers, this is very attractive because basically if you want to save hardware, you realize that your encryption hardware is identical to your decryption hardware. So you only have to implement one algorithm and you get both algorithms the same way. The only difference is that the functions are applied in reverse order. Okay, so this Feistel mechanism is a general method for building invertible functions from arbitrary functions f1 to fd. And in fact, it's used in many different block ciphers. although interestingly, it's not actually used in AES. So there are many other block ciphers that use a Feistel network. Of course, they differ from DES in the functions F1 to FD, but AES actually uses a completely different type of structure that's actually not a Feistel network. We'll see how AES works in a couple of segments. So now that we know what Feistel networks are, let me mention an important theorem about the theory of Feistel networks that shows why they're a good idea. This theorem is due to Luby and Rockoff back in 1985, and it says the following. Suppose I have a function that is a secure pseudo-random function. Okay, so it's indistinguishable from random and happens to act on n bits. So it maps n bits to n bits and uses a key k. Then it turns out that if you use this function in 3 rounds of a Feistel network, what you end up with is a secure pseudo-random permutation. In other words, what you end up with is an invertible function that's indistinguishable from a truly random invertible function. And I hope you remember that the definition of a secure block cipher is that it needs to be a secure pseudo-random permutation. So what this theorem says is if you start with a secure pseudo-random function, you end up with a secure block cipher. Basically, that's what this says. Now let me explain in a little bit more detail what's actually going on here. So essentially, the PRF is used in every round of the Feistel network. So in other words, here what's actually computed is the PRF using one secret key, K0. Here what's computed is the PRF using a different secret key, of course applied to R1. And here we have yet another secret key, K1 applied, K2 applied to R2. And you notice this is why basically this Feistel construction uses keys in K cubed. In other words, it uses 3 independent keys. So it's very important that the keys are actually independent. So really we need 3 independent keys, and then we end up with a secure pseudo-random permutation. Okay, so that's the theory behind Feistel networks, and now that we understand that, we can actually look at the specifics of DES. So DES is basically a 16-round Feistel network. Okay, so there are functions F1 to F16 that map 32 bits to 32 bits, and as a result, the DES itself acts on 64-bit blocks, 2 times 32. Now the 16 round functions in DES are actually all derived from a single function f just used with different keys. So in fact, these are the different round keys. So ki is a round key, and it's basically derived from the key k, derived from the 56-bit DES key k. Okay, now I'll describe what this function f is in just a minute. But basically, you see that by using 16 different round keys, we get 16 different round functions, and that gives us the Feistel network. So just at a high level, how the DES works, basically you have a 64-bit input. The first thing it does is this initial permutation that just permutes the 64 bits around, namely it maps bit number 1 to bit number 6, bit number 2 to bit number 17, and so on. This is not for security reasons, this is just specified in the standard. Then we go into the 16-round Feistel network that actually you now know how it works. Basically uses the function f1 to f16 as specified before. And then basically we have another permutation. This is called the final permutation. That's just the inverse of the initial permutation. Again, it just permutes bits around. This is not necessary for security reasons. And then we finally get the final outputs. Okay, now as we said, there's a key expansion step, which I'm not going to describe. But basically this 56-bit DES key is expanded into these round keys, where each round key is 48 bits. Okay, so we have 16 48-bit round keys, and they're basically used in the 16 rounds of DES. And then when you want to invert the cipher, all you do is you use these round keys, these 16 round keys, in reverse order. Okay, so now that we understand the DES structure, the only thing that's left to do is specify the function capital F. So let me explain how this function works. So basically it takes as inputs its 32-bit value, let's call it x, but in reality you remember this is R0, R1, R2, R3, and so on and so forth. These are 32-bit values. And then it takes also a 48-bit round key. So here we have our key ki, which happens to be 48 bits. The first thing it does is it goes through an expansion box. And this expansion box basically takes 32 bits and maps them into 48 bits. Now all the expansion box does is just replicate some bits and move other bits around. So for example, bit number 1 of x is replicated into positions 2